And this is the part 2 video to my spring 2018 MA 162 exam 1, where I go through questions 7 to 12. For question 7, we're given two functions. We were to find the area bounded by those. So first, for these, definitely graph them. So we have, first of all, graph the easy one. Y equal to negative 2x. So it's just something like this. Just a straight line down with slope of -2. The second one is a little harder to graph, but I tend to use the trick for these. So for quadratics, the middle line, the symmetry line is -b over 2a, I believe, and that is what negative 4 over 2 times 1, so it's 2. So it's centered around, let's say it's 2 right here. Right, and then the other thing is we gotta calculate a few points. We can do that, um, just hit two birds with one stone and calculate the intersections between these two functions. So make them equal to each other. I have x squared minus 4x equal to negative 2x, plus 4x to both sides, x equal to 2x, right? So here we can see that if you divide by x equal to 2, but then you have to worry about x equal to 0. So x equal to 0 is definitely option 2. So we have x equal to 0 and x equal to 2. That means they intersect at these 2 points. Since we already have the function graph right here, we can say that it intersects, this parabola intersects this line right here at 0, 0, and it intersects right here at 2, -4. Right, so you plug in 2 here, you get -4 and 0 for 0. So then, now since this parabola has a positive first term for first constant, the opening is upwards. So generally, the shape will be something like this, right? So before the line, it's steeper, and after, it gradually hits the trough here and goes back up. Right, we're only concerned about this part, the area in between. So whatever happened here, it doesn't really matter to us. Right, so now we have it visually figured out. We can see that the black line here, the line is above the parabola. So let's write the integral for that. Right, so we have top minus bottom, -2x minus x squared minus 4x. Of course, dx. And from we calculate here are the intersections of the two functions, which will be our limits of integration from 0 to 2. Right, from 0 to 2. So here, simplify a little. Bring the x squared term up front, and this will be plus 4x, so plus 2x dx. Now do the simple integration. So this will be negative third x to the third plus x squared. Evaluate it from 0 to 2. And so this would be negative 8 over 3 plus 4. Then it would be plus 0 minus 0, which doesn't matter. So here would be, let's be negative 8 over 3 plus 12 over 3, which is positive 4 over 3. So for question C, B would be correct. For question 8, we are again given two functions. So this time, it seems like their um, dependent variable is x rather than y in most cases. So again, we will just try to draw this the normal way, x and y here. A little bit tricky for the second equation, but the first equation, x to y, simple enough. The second equation looks a little bit tricky, and it would be something like a parabola going this way, right? Either this way or this way. Since the first term here, the square term is actually positive, so we can say that it's going this way because it will be with positive y, you get really positive x. So you can see that it's going to go that way. So positive x and positive y will go together. So now, where do we graph this? So first we can get a couple points, right? Again, we would use the trick from number 7 where I just find the intersections and find the points that I want. So I made them equal to each other. So now y equal to y squared minus 2y. So then here move the 2y over. We get y equal to 3 or equal to 0 or equal to 3, right? So y equals 0. This equation will stand, and divided by y, you get 3. So now we know that it intersects this line at 0, so right here, and intersects at y equal to 3, probably somewhere right here. Now again, the symmetry line can be used too here, except y will be our x, so negative b over 2a, we have negative 2 over 2 times 1, so you can see the symmetry line is actually on y equal to 1 rather than, so here's 1, 2, 3. Since it's symmetry, we can say that 1 away from 1 at 0, it crosses the y-axis. Therefore, at y equal to 2, it also will cross this y-axis at x equal to 0. So now generally, since we have the shape of the parabola pointing towards this way, we can generally fill in the shape using these 3 points. Right, it will hit something like this, and then come back up. So now, we can see that this is the area we're working with. And if we look at a dy point of view, we can actually see that if you tilt your head 90 degrees to the right, you can see that the first function, x equal to y, would be the function above the parabola. So we can write the integration here. Let's see. So y, remember this, I will want to take dy for this since dx will be a little tricky. Y minus y squared over minus 2y dy. And here, again, the limits of the integration will be 0 to 3. Simplify a little. Plus 3y dy. So this would be 0 to 3. And then just plug in. That would be 27, negative 9, plus 927 over 2. 9 over 2 will be our answer. But I want to go more in depth on um, dy stuff because I know that's a little bit confusing. So let's just go back. I'll use a different color. So if we were to choose dx in the switch situation, we'll have to consider that um, it would be the y's that we're looking for, since we're dividing this area into infinitesimally small x's, right? So really small x regions. Right? That's the idea of dx, and the idea of calculus divided into really small spaces where we can just say the y's is the what's matter and then times the dx here. So that means that we have to divide something like this, right? These little sticks of um, yellow dx's where it's pointing upwards. And you see the problem here then is with that for this part, use another color. For this part, um, this region is bounded by the same function above and bottom. So now you need to do some square roots and then do, I don't know, it would be square root of something. This is a square root function. And then minus, and then your integration would be like this function, square root of something, minus square root of something. It would be negative of that, so it would be plus, but it would be the below part. So that's a pretty hard part. Like this part is the same, right? This part, you will have the parabola minus the line. But now, if you were to use, oh boy, that erases everything. I'll just draw this using the black line. dy, then we look up, the point of view of things is now, since we're dividing y by infinitesimally small, so now we're looking this way, horizontally, these little sticks of x values that we really add up. So now the whole region that we're looking for are bounded on top by the same function, right? All of this is on top is the line, and all of it on the bottom is the parabola. So now it's just one integration will do the trick. Another way of thinking of this, if this is too hard, is that you can just redraw this and just put the x on the y-axis, put the x on the vertical axis, and y on the horizontal axis, right? Y equal to x still doesn't change, like so, right? So we have 1, 1, 2, 2, 0, 0, stuff like that. It's the same. Whereas here, you just really got to swap the x and the y's, and then you can get something like this. Really bad parabola drawing, but you get the idea. So now it's this region that we're looking at, right? It's bounded by on the top by the line again, and bottom by the parabola. And then now you can write, so 0 and 3, the limits doesn't change, right? The top is x equal to y, and then minus the bottom one, which is y squared minus 2y. And remember dy, since we're going this way, which is on the y-axis, dividing the y-axis into really small pieces. And this, you would notice, is the same as this function over here. So you can flip the axes, but sometimes it might be a little confusing, I will have to admit. So some practice with this will be nice. For number 9, we're to use distance washer for these two functions and find out the resulting solid that's revolved around the x-axis. So first, let's graph the two functions and take a look what is here. So first, graph the line first. That's somewhat of a line. And then here, we have the parabola. And now, since it's revolving around the x-axis, it's this part that is revolved around x-axis. So it would be doing something like this, right? So just use a different color. It'll be revolved over. So the line will be here, right? With the area over here. So in general, we can think about this as the solid. Since the line is on top, somewhat a solid like this, right? Here's the x-axis and the y-axis. And then minus out the solid that's here, right? Resulting in whatever this thing is, which it would be something kind of like a dome with a middle taken out. But the point of this is that now we can see that it's capped by the line on top, and then the parabola on the bottom. So we can write our integral. It'll be something like pi r squared. So the radius of the top one squared, which would be 2x squared, minus x squared dx. And we can find the limit of integration by, and again, making these equal to each other. And then we can see that x equal to 0 or 2. So here, simplify a little. 4x squared minus x to the fourth dx. So yeah, it would be option E. But here, the pi r squared really comes from the area of a circle, since it is revolving around the axes. You can really think of these as, so if you look from this view, let's say like you are standing over here, right? You're looking into the graph that's revolving around. So what you see would be something like this, right? And then with a little pointy end. There's not really a good way of drawing this. But the pointy end is here, right? And then it opens up. Right, it opens up. So this is like these parts. But you can see that these are really just circles. So what we're essentially doing here is just taking a little bit at a time. This is the dx part. And every little bit of the circle, we're saying that since the circle has two parts, right? It's capped outside by the line and then inside by the parabola. We're taking the area in between those. That's why we have pi r squared of the outside. Rather 2x squared. Make sure I get the right colors. Right, so for the outside it's a line, so it's pi squared. So that's the area from of the circle like this, right? And then minus the inside area, which is the purple area, which is pi r squared of the parabola. So that's why we have this function. Essentially, we only want the middle area. We're doing that by minusing the inner area from the outer area. Now question 10 is exactly the same question, given two same equations from question 9, but now we're using cylindrical shells. So again, let's draw this. Right, we'll have the parabola and the line. Revolving this area around. So again, the same graph. You revolve over here and something like this. But now we're using cylindrical shells, which in this case, it would be really the length of x at each shell. Right, so now going back to that graph that I drew earlier, where some guy is standing here looking in. So you see something like this again, right? Except this time, we're gonna see it from this perspective, sideways. So now it's something like this. Right, middle, there's like some empty spots, like here. So now, what we're doing is taking these shells, right? Each shell, like so, and we drop it down. So each shell has like infinitesimally small width, but then we can use each shell will be what 2 pi r times h, and then with the dy in this case, we can then calculate the volume since we're taking it very small and then calculating each single shell of like this. So in this case, we have to sort of flip the dependent variable. So the two equations would be x equal to square root of y and x equal to y minus 2. Since we're doing dy, cylindrical shells need to go this way. And now we can say that the cylindrical shell height is really the top minus bottom. So say h equal to square root of y minus y over 2. And then if you notice, the radius in every single one of these is just a y value. So at this point, this cylindrical shell has the radius of this much. It's just a y value of this part, right? Because it would be something like here and here. So we can then write our integral, be the same thing. Actually, just write the inner part first times the r, which is y, times the height dy. Now we gotta get the y values, right? So we have root y equal to y over 2. Square both sides, 4, so y equal to 0 and 4. Right, we have multiply both sides by 4, and 4y equal to y squared. So it will be 0 to 4 rather than 0 to 2. And here we can see that looks like B will be the correct answer. For question 11, we're given a few equations and asked to find the C, the positive constant C that will make a certain volume. In this case, will be pi. So first of all, again, let's draw what this will look like. Right? So we have x equal to 0. So just the y-axis, let's label it 0. And we have a certain C right here that we don't know. This will be x equal to C. And let's make, just using red is fine, exponential function, looking somewhat like that. So, in this case, the area we were revolving around the x-axis would be this area, right? Bounded by the x-axis, the two vertical lines, and the exponential function. So if we revolve it all the way around, right, so it make generally a shape like this. So this is just a simple sort of disk method, except we have a unknown here. So generally we just approach this the same, right? An integral, so we have pi r squared for the volume, and then times dx. So pi r in this case would be our y, the exponential function, since it's the y value here. Every time the radius of the disk would be bounded by this exponential function. So pi r squared dx. And the bounds are 0 to c. We don't know what c is, but let's just keep it at that. Simplify a little. E to the 4x. Right, so it's equal to 2x times e equal to 2x. So it's equal to 4x dx. And then chain rule, pi over 4 e to the 4x, evaluate 0 to c. And if plug in c here and 0, we have 4 pi equal to 4c minus 4 pi equal to 0, which is 1. But we were given that this volume equal to pi. So we can say, maybe over here, that pi over 4 equal e to the 4c minus pi over 4 times 1, which is pi over 4, equal to pi. So add pi over 4 to both sides. We have pi over 4c equal to 5 pi over 4 times 4 and divided by pi on both sides. So I get rid of all these things. We have e to the 4c equal to 5. And I take the natural log of both sides. So then we have natural log e to the 4c equal to natural log of 5. So 4c equal to natural log of 5, and c equal to 1/4 natural log of 5, which will be answer choice E here for question 11. For number 12, we have an unusual pyramid of height 2, and we're given the function to calculate the square, the side of the squares of each level of the z, and we are to calculate the volume of this pyramid. At first, this question can be seen as pretty hard to understand. In fact, I had to read it a couple times, but I will assure you that understanding this is the hardest part. So first of all, I begin by drawing just a XYZ plane. XYZ is no longer a plane, a graph. So for this sentence, right, the cross-sectional area for z more than 0 is whatever root 2 minus z. So I interpret it like, so at z equal to 0, so basically at the xy plane, there's a square. I should use a different color. There's a square with the side being 2 minus z. In this case, it would be 0. So this square has size of root 2. And if we go up a level, let's say we are at z equal to 1 now. So here, there's a square smaller with root 2 minus 1, right? So this square has area, rather sides of 1. And we can see that at z equal to 2, right, the square no longer exists since it's 2 minus 2, square root of 0, it has a side of 0. That would be where like the top of the pyramid would be. So if we do some think this in terms of calculus, right? So in very small increments, we can sort of fill in this pyramid here. If you can imagine a pyramid that forms, right, every increase in z, it just kind of gets smaller and smaller, right? The sides get smaller as z increases until 2 it disappears. So just imagine like a pyramid like so. Right, and the concept here is same as any other calculus volume, right? So you have a area that you know, right? But the area of every level of square is just the side, let's say the side is L, right? It's just area equal to L squared. Right, so each area in this case would be 2 minus z squared. And then we use dz in this case, right, times the dz. We integrate over dz, then we can get the whole volume. We're accounting for every single level from 0 to 2 in this case. So with that in mind, let's just write the integral. We have volume equal to the integral of the area, which will be L squared times dz. And this will be from 0 to 2. So simplify the insides a little. It'd just be the square root and the square cancels out. 2 minus z. Simple integral. Oh, no longer an integral. So 2z minus z squared over 2. And value of 0 to 2. Right? And then 2 times 2. 4 minus 4 over 2 is 2 minus 0 plus 0. Then we have the final answer as being 2. So yeah, this question, the hardest part is really getting this graph. And the rest, the integral itself is pretty simple. Thank you for watching this video. The past exam archive and all the videos I did related to this exam will be linked in the description below. Please check them out if you're interested. Thank you.